Okay, everyone, so we're going to start looking at balancing redox reactions. So we're going to do this over a couple of days since there's two different methods to learn about. So today we're going to look at the oxidation number method, and the second method is called the half reaction method. They're similar but different. So we're going to learn one, you'll have time to practice, and then we will do the second one the next day. Okay, so just a review of what we've already covered. So from last week, we talked about how to assign oxidation numbers. So remember that oxidation numbers are the apparent charge that an element would have in a molecule or an ion. And of course, please review the rules we talked about for assigning oxidation numbers. Okay, so remember, anything in its elemental state is a 0, and then here we have a couple of simple ions. Okay, so when we're doing the redox reactions, we have one species or one element that is doing oxidation, which means that it is losing electrons, and one substance that is doing the gaining, which means that it is going down, right? It's gaining electrons, so it's going down in oxidation number. So just to recap, right? So Leo, losing electrons is oxidation, and then of course reduction is our GR portion. Gaining electrons is reduction. So when we talk about balancing, a properly balanced chemical reaction for redox means that the total number of electrons that are being lost has to equal the total number of electrons being gained. So meaning, if something is going up in oxidation numbers, there has to be something else that's going down by the same number. So something is losing 2 electrons, something else has to be gaining those 2 electrons. They can't just all of a sudden disappear or appear out of nowhere. So we're going to go through, I'm going to just quickly go over the steps. These won't really make a whole lot of sense until you start looking at the examples that we have here. So the first step when you're balancing using this oxidation number method is, of course, you have to assign oxidation numbers. So you're going to go through every element in every compound or molecule or ion, whatever the case may be, needs to have a number assigned. So that way, in number 2, what you're going to do is you're going to have to look to see, well, what is changing? Something will be going up, meaning that it is going to be losing electrons, and there's going to be something else that's going to be going down, which means that it is gaining electrons. So then we're going to determine how many electrons have been gained or lost. So actually, numbers 1, 2, and 3, we've already done a few times in the examples from the last section of our textbook. Okay, so here's where we're going to start now looking at balancing this out. So what we need to do is we need to make sure the number of electrons is the same. So what that means is you have to figure out what ratio of those 2 elements that you're going to need to make them the same. So let's say I had one element A that is gaining 2 electrons, and I have element B that was losing 3 electrons, let's say. So the ratio I would need to make them the same, so let's say this was A was, I forgot what I just said, but let's say A was gaining 2 and B was losing 3. We know these have to be the same. I can't have one thing gaining 2 and one thing losing 3. So by the ratio, what I mean by that is essentially you need the lowest common multiple. So in this case, I would need to have 3A for every 2B. That way I'm going to have a total of 6, oh god, goodness. I'm going to have a total of 6 being lost and 6 being gained. So that's what I mean by ratio. Again, it'll make more sense once we start looking at examples. Okay, so then what you're going to do is once you've figured out your ratio of your 2 species or molecules, I say species because really it could be an ion, a molecule, an atom, whatever it happens to be, you're then going to make sure that that actual element is balanced on both sides of the reaction. And then we're going to balance out the other atoms Okay, so it's important to note we're going to leave oxygen and hydrogen for the end. So what I mean by number 6 here is you're balancing anything else. So if there's like chromium or fluorines, whatever else happens to be there, you're going to leave oxygen and hydrogen for the end. Okay, so here's also where it's going to get a little different. We're going to then balance out any oxygen atoms by adding waters. Okay, so again, this is something that's strange, and I know that this balancing approach is different than what you're used to seeing. But redox reactions are a different type of reaction altogether. So instead of changing the coefficient to make your oxygens balance, what you're going to do is you're going to add waters to whatever side is lacking in oxygens. Lastly, you're going to then look at your hydrogen atoms. If you need to balance them, you're going to add hydrogen ions. So instead of changing coefficients to add more hydrogens, you're going to just simply add in hydrogen ions. Now, the reason why we don't want to start changing coefficients for these elements here is because we've already done the coefficients to balance out the electron movement. If we start changing the coefficients in the reaction, we're going to throw the electron count off. So you want to have more of that element, but we're not necessarily going to be changing the molecule that's involved in redox. And of course, pretty much every redox reaction happens in an aqueous solution, which means water is present and hydrogen ions are present because we know that water does autoionization with itself, right? So like the hydrogen is essentially like our hydroniums, and that was from our last unit. So let's take a look. So this first one is already done in for you. So I'm gonna kind of walk you through this verbally. And then there'll be one that you can try on your own. You'll pause the video and then give it a shot. So this says we have the combustion of ammonia in oxygen produces nitrogen dioxide and water. So here's our unbalanced reaction. So the first step is you go and you assign an oxidation number to every single element here, which we're used to doing at this point in time. So remember, if it's a neutral molecule, they have to add up to 0. So hydrogen's +1, that's +3, so that means nitrogen has to be -3. Oxygen is in its elemental form, so it's a 0. Here we have oxygen being -2, so that's -4, so nitrogen is +4 to balance that out. And then, of course, our water is regular hydrogen and oxygen. Right? So what is changing here? We have oxygen that's going from 0 to -2, right? We can even look at it this one, they're the same thing. So we're going down by 2. So oxygen decreases by 2, so it's gaining 2 electrons. Nitrogen is going from -3 to +4. So what that means is nitrogen is losing electrons, and it's actually losing quite a bit. It's losing a total of 7 electrons, right? So we have nitrogen that's going up by 7 and oxygen going down by 2. So what we need here is we now need to make these values the same. Okay, but one thing to keep in mind is how many you have of these elements. So for example, oxygen, there are 2 of them doing this. So technically, we really have oxygen gaining a total of 4. So you always start off by assigning it like per element. But you have to consider, just like when you write out the half reactions, you have to consider how many total electron changes there are. So oxygen, really there are 2 of them. Each one is gaining 2. So in total, we have oxygen gaining 4. And nitrogen, of course, there's only 1, so nitrogen is losing 7. So what we need to do is make that number the same. We can't have oxygen gaining 4 and nitrogen losing 7. They have to gain and lose the same amount. So that's where our ratio is going to come in. So we need to have a ratio of how many we would need. So here we have, we're just restating this. So nitrogen is losing 7, oxygen is gaining 2. So the lowest common multiple here is 14. right? So we would need to have 2 nitrogens and 7 oxygens to make them both be a value of 14. But keep in mind that we have 2 oxygens doing this. So technically, we would need to have 14 oxygens in total and 4 nitrogens in total. So let's go back here for a second. So we have 7 versus 4. So our lowest common multiple here is going to be 28. So we would need to have, so 28 electrons total. So I would need to have, essentially, oxygen having 28 electrons being gained and nitrogen having 28 electrons being lost. So what that means is I need a total of 7 oxygens, because 7 times 4 is 28, and I would need a total of 4 nitrogens. 7 times 4 is 28. So that's why here, if you look at the coefficients we've put in, we have, if you look at this, right? So we have 14 oxygens. So think about, so 14 oxygens, each oxygen is gaining 2. So each oxygen is gaining 2, there are 14 total. That's going to give us a total of 28. Nitrogen, we have 4. 4 times 7 is 28. So normally, I chose a more complex example here because you had to consider that there are 2 oxygens doing this. If this was a little bit more simplified and it was just 1 and 1, then you would need 2 nitrogen and 7 oxygens to get to 14. But because there's 2 of them, you need to double up. So that means we need 14 oxygens and we would need 4 nitrogens. You'll see what I mean in the next example. So in this case, our ratio is, our coefficients are 4 to 7. Now the next part is to balance the nitrogen and oxygen on the product side. So because we have 4 nitrogens here, we would add a 4 in front of NO2. And we need to make sure that we have a total of 14 oxygens on this side. So by having the 4 there for the nitrogen, that means that we have 8. So we would need 6 more, which is why we have the 6 in front of our water. So in this case, we would have to do a check. So we would check. So our nitrogen and oxygen are the actual redox people. They're our participants. They are balanced. So then we would check oxygen. Oxygen here we have already balanced because it actually happens to be part of our redox reaction. And then we have our hydrogens. So let's check hydrogens. We have 4 times 3, so we have 12. Over here we have 12. So in this case, this is perfectly balanced. We have 28 electrons being gained, 28 electrons being lost. Our oxygen and hydrogen count is equal. So this is good to go. All right. So example number 2. So I want you to follow along with the steps that we have so far. So assign your oxidation numbers, check to see what the numbers are changing by, get your ratio in, give it a try, press pause. Actually, I'll start a new video, so we'll stop here, try this example out, and then start the next video to see how to go about doing this.